Yeah, so let's get started. Now people are still dropping in. I think Yin, you wanted to start off with a short introduction.
Sure. Hi, everyone, and welcome. Thanks for joining us today for the second ECS-Precip Seminar of the year 2025. I'm Yunjin Lee. I'm the chair of ECS-Precip subcommittee. Before we start the seminar, I just wanted to briefly introduce ECS-Precip. We are one of the subcommittees of AGU Precipitation Technical Committee, composed of early career scientists and students. Our main goal is to provide useful information to students and early career scientists in the precipitation field. We try to inform precipitation-related conferences or papers, and we try to help create connections between students and early career scientists in the field. And this seminar is part of our main efforts, and it's the second seminar of the quarterly seminar series. Following the first seminar, which was held in March, this seminar will also feature presentations by the recipients of the AGU Precipitation Student Awards from last year's AGU Fall meeting. We usually give out student awards during AGU every year, and we'll also have another one this year. So if you like to participate in the awards, submit a form through our website. It will be advertised through our social media very soon. We have two more seminars coming up, last one being held during AGU week. So also stay tuned for the upcoming seminars as well. If you want to hear more from us, please join our mailing list or follow us on social media. Today, Linda and Lindsay will be the two moderators of the seminar. So take it away, Linda.
Thanks. And thanks for the introduction. So, good morning, good afternoon, depending on where you are. As Young said, I'm Linda, and together with Lindsay, we're moderating today's seminar. I'm a postdoc at the University of Maryland and at NASA, and Lindsay works in Boulder at the Joint Center for Satellite Assimilation, UCAR. I won't take much of your time though, because we have two winners of student winners. So I think they can present way better than I can. Just some house rules. Each presenter will present for 20 minutes. And we have questions, 5 minutes per speaker, but please hold your questions off until the end of the seminar. So first we have the two presentations, and then we will have time for questions. So the first speaker of today is going to be Jack. And Jack Richter, he works. Oh, where's my screen? I lost my screen. Sorry for the hiccup. There we go. Jack is a PhD candidate at the Department of Climate Science and Space Sciences and Engineering at the University of Michigan. He's working together with Claire in the Cold Precipitation Processes group. And he will tell us more about investigation of atmospheric river snowfall properties using suborbital platforms. So Jack, take it away.
Awesome. Yeah, thank you. Thanks for the introduction and for the opportunity to speak at this seminar series. I'm going to be talking about investigating atmospheric river snowfall properties using suborbital platforms. I'd like to thank my collaborators on this work and also thank the various funding agencies that made this work possible. So to begin, for those of you that may not be aware what atmospheric rivers are, we call them ARs. ARs are long and narrow conduits of enhanced water vapor transport in the atmosphere. And they're called atmospheric rivers because they can transport an equal amount of water as major rivers such as the Amazon or the Nile. And what I'm most interested in with respect to atmospheric rivers is that they are associated with extreme precipitation events, including extreme snowfall. This image on the bottom side of this slide here is showing an example of an AR that hit the Western United States a few years ago. And this is just included to show how large these systems can be and how impactful they can be. In the context of climate change, atmospheric rivers are interesting and important to study because they are expected to increase in frequency with a warming climate. This figure on the left here is from Ashley Payne's 2020 study where they simulated future climate scenarios and looked at like the behavior of atmospheric rivers. And all these regions in salmon colored is where they found that the AR frequency would increase due to climate change. And also plotted on this figure are kind of the associated hazards with AR, such as extreme precipitation, flooding, what we see here is that, the extreme precipitation associated with ARs are also expected to increase in frequency. And if we zoom into the, northern hemisphere, we see that this is particularly true in the Great Lakes region of North America and Northern Europe. So I just mentioned that extreme precipitation is expected to increase in addition to, AR frequency in general increasing. And I want to pivot a little bit to talk about extreme snowfall because extreme snowfall is also important to study in future years with climate change. This figure on the left here from O'Gorman's work in 2014 shows the ratio of snowfall extremes with respect to present day. And what this is showing us is that like in these yellow, orange, and red colors is regions that are expected to see more occurrences of extreme snowfall when compared to present day. And this is primarily due to, when we have global warming, that's going to, reduce the frequency of snowfall in some areas, but where it is sufficiently cold, that additional warming is going to increase moisture availability for extreme precipitation events. So altogether, evaluating extreme snowfall, like for example, during atmospheric rivers or AR snowfall, is needed to better characterize snow and, specifically extreme snowfall in a changing climate. So we already know that atmospheric rivers influence snowfall in a couple of ways. Specifically, they are associated with increased snowfall accumulation and enhanced precipitation rates. But we don't really know why this is the case. And I would suggest that, if we looked at the microphysical properties, it would provide the answers that we're looking for. But no study has extensively examined the microphysical properties of AR snowfall to this date. So by evaluating the microphysical properties of AR snowfall, we will be able to understand why ARs influence snowfall and better understand this kind of mode of extreme snowfall. Thus, to study atmospheric river snowfall events, we employ observations from two GPM ground validation instrument sites that are specifically configured to observe snowfall. The first is located in Marquette, Michigan, which is located in the Upper Peninsula of Michigan on the southern shore of Lake Superior. And the second is located in Hutiala, Finland, which is in south central Finland in Northern Europe. The cool thing about these sites is that they are both located in regions that frequently experience ARs during snowy months. We see here that, with the Marquette site here in the Upper Great Lakes region, and also the Hutila, Finland site in Northern Europe, these are, locations that already experience ARs at a frequency of about 10% during snowy months. And by snowy months, I just mean like any month in which snow is possible to occur in. So we define that as October through April. And if we bring back the figure from Ashley Payne's work, we see that these sites are also located in the regions that are projected to see more frequent and more intense ARs, which further highlights that these are great sites to study AR snowfall. All right, now I'm going to talk a little bit about each of the sites and the instrumentation that we have to study AR snowfall and specifically the microphysics of AR snowfall. So with the first site, it's the Marquette site, which is, as I mentioned, is located in Marquette, Michigan. It's adjacent to the National Weather Service office in Marquette, Michigan, and there are two primary instruments that we utilize there to study snow microphysics. The first is the microrain radar, or an MRR, as we call it. The MRR is a profiling radar that operates at the K-band. And a profiling radar is going to be a radar that scans vertically in a fixed position as opposed to an azimuthally scanning radar that you might be more accustomed to in an operational sense. But the cool thing about a microrain radar is that we get really fine vertical and temporal resolution of the structures of precipitation. The second instrument that we use is the Precipitation Imaging Package, or the PIP. The PIP is a NASA video dish monitor that provides several microphysical products, such as the particle size distribution, the fall speed distribution, and it also provides estimates of the effective density and the accumulation rates of the precipitation. So the precipitation imaging package is highlighted here on the right side of this photo, and it's composed of two components, the first being this high-speed imaging camera, and the second is this bright halogen lamp, and it's orientated such that particles that fall in between the bright halogen lamp and the high-speed imaging camera kind of cast shadows that can be measured and recorded through various imaging processing techniques to give us those microphysical products that we are interested in. So I include this video here to kind of just demonstrate what the PIP sees. This is a slowed down version of the high-speed imaging camera from the PIP. And what we're viewing here are falling snowflakes in the XZ plane. So as I mentioned, there's this bright halogen lamp that is cast on the high-speed imaging camera, and these are the shadows that the particles cast onto the field of view. And if I just kind of aggregate some of the different particles and snowflakes that we see in that video, there's a lot of variability in the sizes, the shapes, the orientations, the concentrations, and additionally the fall speeds of the snowflakes. And those are exactly the microphysical properties and characteristics that we're interested in measuring in this study when looking at AR snowfall. The Huhtila site is in Finland, and they have similar instrumentation as with the Marquette site, so it allows us to employ similar techniques and analysis methods to compare the snowfall at these sites. They also have a profiling radar. They call it the RPG-94, which is a profiling radar operating at W-band. And they also have a PIP, so we're able to additionally get those microphysical products such as the particle size distribution, the fall speed distribution, and also the effective density. All right, now that I introduced the instruments that we use in this study, I'm going to briefly talk here about our snowfall classification scheme that we use to identify the events of interest in this study. Being that we want to study atmospheric river snowfall properties, we need to have a robust methodology for identifying AR snowfall events. And this is going to be kind of a brief overview of this. So the first step of the snowfall classification scheme is the deep snow detection algorithm, which was specifically developed for this study, and it is employed to find occurrences of deep snowfall at each of the sites. Deep snowfall is going to be snowfall that is large scale and synoptically forced in nature, as opposed to like lake effect snowfall or shallow snowfall, which is going to be more mesoscale in nature and not connected to the spatial and temporal scales of atmospheric rivers. This step of the deep snow detection algorithm has two criteria that we're looking for. So to ensure that we're getting large-scale precipitation, we want precipitation ecotop heights greater than or equal to 3 kilometers. And to ensure that we're getting snowfall as opposed to rain, we employ a PIP effective density threshold of 0.4 grams per cubic centimeter. These criteria are kind of outlined in this figure on the left here. So panel A is showing the height time reflectivity from the profiling radar on this date. And what we see here is that these black dots are where the algorithm kind of determined that there was the precipitation ecotop heights. And where we see this kind of like region of precipitation ecotop heights equal or greater to 3 kilometers, we say that that is deep precipitation. And we mark that by the magenta horizontal line here on the bottom of panel A. Panel B is showing the PIP effective density measurements as a function of time. These like blue regions are going to be regions that are indicating solid precipitation, and these red regions are going to be those that are indicating liquid precipitation. So the orange line here is indicating where we have solid precipitation. And thus, the overlap of these two lines is where we define a deep snowfall event, and that's kind of outlined by the cyan box. The second step of the snowfall classification scheme is the AR detection algorithm. We employ the Mattingly AR detection algorithm to find instances of AR overpasses within 100 kilometers of the site. And this panel C here is showing the AR overpass that coincides with the previous slide, that event on the 10th of April 2015 at the Marquette site. So being that this the Marquette site was within 100 kilometers of this AR, we say that the event on that day was a AR snowfall event. And just to summarize a bit, an AR snowfall event is going to be an event that satisfies both of these conditions here, both having a deep snow detection and an AR detection. And the no AR snowfall events are going to be those that only satisfy this first condition, the deep snow condition. So the only difference between these two event regimes is that the AR snowfall events are going to coincide with an AR, and this allows us to really isolate the effects that ARs have on snowfall properties and understand why ARs impact snowfall. All right, now I'm going to get into some results, starting with the mean environmental and bulk physical quantities for each of the two regimes. The two regimes are the AR snowfall events and the no AR snowfall events at each of the sites. So on the left here, we have the physical quantities of interest. We have the two sites noted at the top here with the individual regimes at each site. And going through each of these quantities one by one, we see that the AR snowfall events are warmer than the no-AR snowfall events at each site. They have higher surface wind speeds compared to the no-AR snowfall events at both sites. They have higher near-surface reflectivity values than the no-AR snowfall events at both sites. And they also have higher snowfall rates compared to the no-AR snowfall events at each site. All right, now I'm going to get into kind of the more bulk and composite statistics of these AR and no-AR snowfall events at each site. And what I'm showing here is data from the profiling radars at each site. And what specifically I'm showing is the 2D normalized histograms of radar reflectivity as a function of height. So the top row is going to show the events at the Marquette site, and the bottom row is going to show the events at the Hughes site. And as I mentioned, these are 2D histograms. So we have height above ground level on the y-axis, and we have reflectivity on the x-axis. Panels A, B, D, and E are showing those normalized 2D histograms for each of these individual regimes at each of the site. And panels C and F are where we subtract these at each site to kind of understand the regions that are more characteristic of each of the regimes. And specifically, these red regions are going to be those that are characteristic of AR snowfall, and the blue regions are going to be those that are characteristic of no AR snowfall. And what we observe here in panels C and F is the shift of the red regions to be farther to the right than the blue regions in both of these panels. And since reflectivity is increasing to the right, this is informing us that AR snowfall has enhanced reflectivity throughout the column when compared to no AR snowfall. And this is the first indication that AR snowfall is an extreme mode of snowfall. And when we compare with those values that we saw in the table on the previous slide, the higher near-surface reflectivity values and the higher liquid water equivalent snow rates during ARs further signals this extreme nature of AR snowfall. All right, now I'm going to get into the PIP products, so the products that we get from the precipitation imaging package. The precipitation imaging package is observing the snowflakes as they fall, and so it's giving us those microphysical characteristics of the particles themselves, in this case, the snowflakes. So we have a similar organization as with the previous figure, where we have the Marquette events on the top panel, on the top row, and we have the Huhtala, Finland events on the bottom row. But in this case, we're looking at the composite particle size distribution. So the particle size distribution is a way of relating the number concentration of the particles as a function of size. So on the y-axis here, we have a log base 10 number concentration, and on the x-axis, we have the particle size or its diameter in millimeters. Panel C and F, we do a similar technique where we subtract these histograms. That's kind of shown in this like more transparent, low alpha value pixels. But similar to before, we subtract them from one another to reveal those regions that are more characteristic of each of the regimes. But we also plot the median and then also the 10th and 90th percentile PSDs for each of the regimes at each of the site to give us some more quantitative information. And since the particle, like the number concentration increases as we go to the top of these figures, this shift that we're seeing, and specifically the shift that we're seeing, is these red pixels are shifted to higher number concentrations compared to the blue pixel regions. And additionally, by looking at the median and 10th and 90th percentile PSDs, we see this shift to higher number concentrations. And this is indicating that the AR snowfall events are producing more particles than the no AR snowfall events at both sites. And if we just compare the median PSDs, this is telling us that there's 38 to 47% more particles than the no AR snowfall events at both of the sites. You may be asking what is causing these shifts in the particle size distributions. Well, because the atmospheric river events coincide with these AR overpasses, there's likely more available moisture to nucleate particles in these AR snowfall events, which would explain the shift. And then in these medium size ranges, kind of between 1.5 and 3 millimeters, we have this signal of aggregation occurring, which can, increase the number of particles in these medium size bins. All right, so those were the particle size distributions. And the next PIP product that we're interested in looking at to compare the microphysical characteristics are the fall speed distributions. So this is a very similar organization as with the previous figures, but now we're looking at the fall speeds of the particles as a function of diameter. Additionally, plotted on these panels A, B, D, and E are typical fall speed relations from the literature. And we do a similar differencing approach and also a median 10th and 90th percentile approach as with the PIP PSDs. And we see a similar pattern emerge where we have this shift of both the red pixels and the percentile PSDs to higher fall speeds. And this is informing us that the AR snowfall events are producing faster falling particles when compared to the no AR snowfall events. And if we just tried kind of like eyeballing some of these relations, this is also informing us that the AR snowfall events are more typical of, graupel-like snow and densely rimed relations, whereas the no AR events are going to be lighter rimed and unrimed particles. All right, so the last PIP product that we're going to take a look at here are the effective density measurements and the effective density distributions of the particles as a function of diameter. So as with the PSDs and the fall speed distributions, we have diameter on the x-axis. But in this case, we have the effective density on the y-axis, which is a measure of kind of how heavy these particles are and how fast they're falling through the ground, because the density is going to be directly related to the fall speeds. And we have a similar organization with this. We have the 2D normalized histograms in A, B, D, and E. But what's really interesting here is seeing the same pattern emerge in CNF, where we have this shift to higher values during the AR snowfall events when compared to the no AR snowfall events. And this finding is telling us that the AR snowfall events produce denser particles than no AR snowfall. And specifically, if we relate these shifts to other empirical relations in the literature, we say that these effective density shifts are representative of about a 10% increase in the fraction of riming during AR snow when compared to no AR snow. This is just a further indication that enhanced riming may be present during AR snowfall and may be one of the causes for these higher densities and higher fall speeds. All right, to summarize the work here, we showed that AR snowfall is more intense than no AR snowfall. And this was primarily demonstrated by those enhanced reflectivities that we saw during AR snowfall and the higher liquid water equivalent snowfall rates during AR snowfall. We also determined that there's distinct microphysical properties during AR snowfall, and specifically that they produce more particles, faster falling particles, and denser particles than no AR snowfall, with enhanced riming seemingly to be a potential mechanism that is explaining those faster fall speeds and denser particles. And what I think is really neat about this work is that the results were very consistent between the two sites, which are located in distinct regions, which just highlights the robustness of these results and the methodology. And then the last thing I want to mention is that this work is contained in a manuscript that is currently in revision at GMC. Hopefully that'll be out soon in the next couple of months, so definitely be on the lookout for that. And yeah, thanks for listening.
Thanks a lot, Jack, for this very interesting presentation and for sticking within the time. That's highly appreciated as well. Like I said in the beginning, please hold your questions until the end of the session. So for now, I would like to thank Jack again, and would like to invite Kaidi to present her work. So Kaidi Peng is our second presenter. And she's a third-year PhD student in civil and environmental engineering at the University of Wisconsin-Madison. Her research interests are focused on the uncertainty quantification for satellite-based precipitation data and the impact on hydrologic predictions. And she will tell us about the uncertainty quantification for deep learning-based Streamflow prediction. So Kaidi, take it away.
Thank you. Thank you for introduction. So here I'm going to talk about uncertainty quantification in deep learning-based streamflow prediction. Current global streamflow prediction are inconsistent in accuracy and especially uncertain in developing countries. The thing I'm showing here shows the bias of streamflow prediction from European Center for Medium range weather forecasts. Red dot indicating good model performance are concentrated in CONUS and Europe regions, while worse prediction shown by blue dots are frequently seen in developing countries. This issue may arise from both uncertainty in model and data. Current global streamflow prediction system mostly rely on traditional physics-based or conceptual hydrologic models, which may suffer from inaccurate forces and strong assumptions on governing equations. To partially overcome this, deep learning-based hydrologic model has been proposed. Usually, high accuracy and least computation time are reported, while as we can say, overfitting and least explainability are usually a typical concerns of deep learning models. As a type of hydrological model, deep learning-based hydrological model is not immune from uncertainty. The main input for hydrological model is precipitation. It's usually introduced from satellite-based precipitation products for ungauged regions in most of the world. For example, this slide shows the images from the integrated multi-satellite retriever for global precipitation measurement, iMerge. Studies have shown that these iMerge products have over and underestimates of precipitation like in different regions of the world. Most of the time, when we try to fit a deep learning model, we do not have perfect and infinite data to represent the real world in the model training. So here I introduce a data limitation uncertainty to represent any potential unmodeled measurement errors in the training data, the unknown characteristic of new input data, or limited training data samples used to represent the real-world conditions. Lastly, neural network parameter uncertainty arises from deep learning model itself. Different model parameters and hyperparameters, including hidden layer activity function and so on, are subject to change in model training. In this conceptual figure, 3 sets of possible model hypotheses are selected based on the limited training data we have to make their own predictions, which are indicated by these different color shadows. And its predictions can constitute an ensemble covering both the effects from the limited data and the different model hypotheses. Basically, its ensemble spread obtained from its model training is more likely to capture the ground truth compared to a deterministic training process. These 3 sources of uncertainty, the input data uncertainty, especially for precipitation, model parameter uncertainty, and data limitation uncertainty, they are usually mutually affected by each other, leading to the overfitting issue of the deep learning models. However, up to now, no study focuses on comprehensive uncertainty quantification in deep learning-based Streamflow prediction. So this leads to the objective of my study here. I tried to develop an uncertainty quantification framework for deep learning-based Streamflow prediction, especially for regions without ground-based precipitation measurements. This would include quantified satellite precipitation uncertainty in the absence of precipitation reference, and also try to quantify data limitation and model parameter uncertainties in deep learning trainings. Sorry. Now we come to the methodology part. LSTM, long short-term memory, were selected as my base deep learning methods. This method has been evaluated over the past 2 years. They have shown that LSTM can kind of have a good representation of hydrological model prediction. So we take this as our base deep learning models. Then we further define a gamma distribution to quantify the satellite precipitation uncertainty. But as I said, we do not have precipitating ground truth for most of the regions in the world. So the values of these distribution parameters are unknown. Different parameters may contribute to different precipitation uncertainty distribution that will cause different effects when we use its precipitation to drive the LSTM to predict the stream flow. But furthermore, in terms of LSTM training, the model parameters and any deficiencies in the data is also unknown. For data limitation uncertainty, we use a method called mixture density network. We use LSTM to predict a Laplace distribution where the stream flow observation is the maximal likelihood estimate of this Laplace distribution. The wider the distribution is, the more uncertainty arises from the data. If we have infinity perfect data to train the model, then we can expect this Laplace distribution can almost converge to an exact value. To account for the model parameter uncertainty, Gaussian distribution is taken for each parameter values. So basically, this method is called variational inference. We try to optimize a Gaussian distribution for each parameters in the deep learning models. So each model parameter ensemble member is a sampling from this Gaussian distribution. Then with the different sampling, have different model ensembles, then we can make a different prediction of Streamflow. These different choices of model parameters correspond to different data limitation uncertainty estimates. So, but since we need to estimate these three unknown distribution to represent the three uncertainties, we need Streamflow observations to help us to retrieve them. So this Streamflow observation will be first used to update precipitation uncertainty parameters. This is our out iteration. Furthermore, 100 epochs were employed to optimize the deterministic LSTM parameters under the current condition of precipitation uncertainty. This is our inner iterations. So the optimized LSTM from this inner iteration the Streamflow prediction from this optimized LSTM from the inner iteration will be further used to update the precipitation parameters in the next outer iteration. But typically in this case, we try to estimate both the model parameters in LSTM and the parameters in precipitation uncertainty. But like deal with the two uncertainties in a sequential way. So after we get the LSTM model parameters, then we further include the data limitation uncertainty and the model parameter uncertainties, so that finally we can obtain a Streamflow ensemble estimates. When we try to use the precipitation uncertainty to drive LSTM to predict the Streamflow, we use 5 quantiles of precipitation uncertainty distribution from 0.1 to 0.9 to be used as a precipitation functions. But since we have different 3 pieces of uncertainty in our modeling framework, we need to understand how these different uncertainty pieces affect the accuracy of our Streamflow prediction. So I made a couple of comparisons. First, this undetermined satellite-based precipitation uncertainty as functions is the method that I mentioned in the last slide. So basically, this satellite-based precipitation uncertainty will be estimated during the LSTM model training. The true satellite-based precipitation uncertainty is also presented by a gamma distribution, but the parameters are estimated based on precipitation ground truth. So it's kind of a best case we can have for precipitation uncertainty. We will compare the retrieved precipitation uncertainty from LSTM model and this precipitation uncertainty ground truth to evaluate whether our method can retrieve physically plausible precipitation uncertainty. I also use those satellite estimates, emerge, and precipitation ground truth as the precipitation functions to drive LSTM with different uncertainty pieces considered, so that we can try to evaluate whether our uncertainty quantification method can help to enhance the explainability of deep learning and reduce the overfitting of deep learning models. So this framework will be experimented in one of our study watershed, which is located in the southeast North America. So its size about 700 miles squared. We make hourly stream flow prediction for this study. So we take hourly and watershed average the precipitation and other forcings to achieve LSTM. Now we come to the results part. So we first here look at the retrieval of precipitation uncertainty. So here I compared the cumulative distribution function of estimated precipitation uncertainty and precipitation uncertainty ground truth on condition of different emerge observations. The black shaded line is the emerge observation. You can see the ranges from 0.1 to 10 from the top to the bottom. So as the emerge values increase, the shape of the CDF move towards the higher precipitation values. The red solid line here is a CDF from the precipitation uncertainty ground truth, which is the precipitation uncertainty that we estimated using precipitation ground truth. The blue line is the estimated precipitation uncertainty from LSTM training. So we basically can say the blue line generally close to the red line. But we also think that there may be a little bit underestimate of precipitation values for these bottom fingers for higher precipitations. So this may due to the limitation of we trying to using stream flow to retrieve precipitation, or maybe because in LSTM we need to rely on the correlation between precipitation and stream flow to recover the precipitation properties. So in this case, the loss of precipitation due to infiltration or evaporation cannot be explicitly modeled. So from LSTM, we're very likely to only estimate the effective precipitation, which is a part of a precipitation that will finally contribute to the stream flow in its watershed. But generally, we can say that the true precipitation uncertainty can be approximately recovered from LSTM training. But this method, as I said, needs some statistical correlation between stream flow and precipitation. So we basically found that its method works better in smaller watershed, where the contribution of precipitation to stream flow is stronger than the larger watershed. Now it comes to the results for stream flow prediction. And we try to evaluate the importance of different uncertainty quantification pieces. So we show two types of fingers in this slide. The left one is the standard deviation plot, which compares the root mean square error, RMSE, of the ensemble mean against the standard deviation of the ensemble. A line closer to the one-to-one diagonal line indicates that the stream flow ground truth stream flow observation is statistically indistinguishable from each individual ensemble members. And if we see a larger standard deviation from this finger, it usually means we have over dispersion in our predicted stream flow ensemble. But if we see a higher RMSE in this finger, basically it means we get a larger errors in our prediction, and we very likely to under dispersion the ensemble prediction. So the right hand side we have a finger for KGE, which is usually used to evaluate the accuracy of each stream flow prediction ensemble member. So the KGE is calculated using stream flow observation as a ground truth. The best value for KGE is 1 and the worst is negative infinity. So here we have 4 different cases to be evaluated. Basically from bottom to top, there is only one line here, the one dot here is a deterministic streamflow prediction that we do not consider any uncertainty in the modeling process. The blue one is the situation that we only consider data limitation uncertainties based on a mixture density network. The yellow one is a streamflow prediction that we only consider the model parameter uncertainties using variational inference. The top red one is the streamflow prediction where we consider both the uncertainty from model and data. So currently, the 2 fingers are the results driven by precipitation ground truth. We typically can say that when we consider the data limitation uncertainty of both uncertainty, we can have a prediction that align with the one-to-one reference line in our standard deviation plot. But if we only consider the model parameters uncertainty, we're very likely to get under dispersion, and the prediction errors might be larger. So this means that when we try to, if we only consider model parameter uncertainty, we're very likely to deteriorate the model prediction during medium to larger flows. As in high flow prediction, the data uncertainty is the most important one. In right-hand side, we can say if we consider both uncertainty from model parameters and data limitation, we get the best KGE values in all these cases. Now we can also look at the streamflow prediction from row satellite estimates, I-merge, or from the precipitation uncertainty estimates. So we can say even though we consider both data and uncertainty in I-merge cases, we still get higher errors in high flows during in this standard deviation plot. So this may due to the errors in I-merge, especially for high precipitation values. But if we consider the precipitation uncertainty in our case, then in this bottom finger, we can say when we consider both model and data uncertainty, we get a plot that very close to the one-to-one reference line in this standard deviation finger. But in terms of KGE value, we didn't see any significant improvement compare the streamflow driven by precipitation uncertainty and the streamflow driven by I-merge. This may mean that during LSTM training, the LSTM model can kind of partially learn how the I-merge uncertainty will affect the streamflow prediction, and the model will try to regulate its parameters to account for the errors and I-merge. But if we use precipitation uncertainty estimates as the precipitation forcings, and the model will try to separate the precipitation uncertainty estimates part from the model training, so that we can get a physically reliable precipitation uncertainty parameters from our methods. But basically, we can say reduced overfitting can be achieved by considering both data and model uncertainty. So this is only some part of finger that we use to evaluate the differences between these uncertainty components. We can also try to look at how the model performs during different streamflow quantiles. But from account experiments, basically can say if we consider both uncertainties, we can get a better estimation, especially for high flow events. So that's really what we want to be used in flood prediction. So furthermore, we look at the expandability of precipitation uncertainty. So here we
Kaidi,
calculate.
just a heads up. You have 2 minutes left.
Yeah, sure. Got the end. We have the Shapley values attribute the contribution of each feature, each forcings to the model's prediction. A larger Shapley value means a stronger contribution. All forcings, including precipitation, temperature, pressure, radiation, wind speed, and humidity, are evaluated here. So you can say for ARC-driven streamflow, the effects of precipitation is kind of 3 times larger than other forcings. But if we're using I-merge as the precipitating forcings, ranks of precipitation become the second one, and its effect is much lower than the case that we use ARC as a precipitation forcing. But if we use precipitation uncertainty to drive streamflow, we can the effect of precipitation uncertainty is actually distributed over our all precipitation related input, which is our 5 quantiles from 0.1 to 0.9. But basically, we can say in this case, the effects of precipitation uncertainty kind of gets a little bit larger than the one from the I-merge. So it's still a little bit of the contribution is still a little bit lower compared to that of ARC. But since we have make the precipitation is more important than I-merge in our streamflow prediction. So we improve the explainability of precipitation uncertainty in LSTM. Now we try to make a summary. I developed a framework that is able to provide precipitation uncertainty quantification without precipitation ground truth. Our framework investigates the extent to which an LCM can internally learn and represent the precipitation uncertainty during the model training process. Considering both data and model uncertainty in deep learning-based streamflow simulation is important to reduce the overfitting of deep learning. But since at this time we still rely on streamflow observation to get our uncertainty components, so moving towards already engaged regions, we will consider to involve the satellite-based streamflow estimates in our framework. But in this case, we need to further consider any uncertainty in the satellite-based streamflow estimates. But that would be not difficult to be included in our model because we can just model one more uncertainty components and put it into our framework. Yeah, I think that's all for now. Thank you all for your listening. I'm happy to take any questions.
All right. Thanks so much, Kaidi and Jack. Does anybody have any questions for our speakers? We have about 10 minutes left. Yeah, Eugene, go ahead.
Jack, thanks for the great talk. I have a question for Jack. You mentioned at the end that the results were pretty consistent between 2 sites, and I was wondering if you've observed any unique features at each site other than the main results.
Yeah, so some of the differences between the sites I didn't necessarily show, but there were some pretty stark differences in the synoptic scale characteristics. So for example, in Marquette, there was I evaluated the kind of anomalies of the synoptic setups, and in Marquette it was more about the location of high pressure kind of steering cyclones towards the Marquette site. But in Finland, it was more so due to kind of extensions of the North Atlantic jet stream and also some Atlantic trough patterns. And then otherwise, just in general, the events at Hutila, in the Finland site, were a little bit less extreme compared to the Marquette site.
Thanks.
Go ahead, Daniel.
I don't know if you can see me and
Yep.
hear me. Okay, great. I have a question for Jack as well. So really nice talk, both Jack and Kaidi. Jack, my question is, so obviously you found these like great differences between different types of snowfall events, and in particular in the microphysics. What's the impact of your work going forward then? So where do you see this, being fruitful? Does it go into climate models? Does it go into, addressing algorithms? How do you see it?
Yeah, so I would say the microphysical differences are exactly things that you would want to take account for in your parameterization schemes when you're trying to model ice microphysics, especially if they're subgrid processes. For example, like the next steps would be kind of trying to better understand the processes instead of the properties. So this work was more so looking at the bulk characteristics. So for my next project, I'm going to be looking like kind of in the column with aircraft data to try to see if we can like explicitly say that there's like certain processes occurring. So like we can like kind of put flags in for like if we see these specific conditions set up, for example, with like the atmospheric rivers, we can choose like a specific way to model them.
Okay, and just to thank you for your answer, and just to follow on from that, then, so obviously, you're seeing key differences between different types of snowfall events. So obviously, you're saying about looking at the column as well. Is there a chance that you'll look at just different kind of stratifications now to see if there's different things going on? So say by latitude or by different type of events.
Yeah, so the primary way I'm going to stratify the observations is going to be by the environmental conditions. It could be very useful to look at different latitude bands, but it definitely when you're looking at the column with like aircraft campaigns, it definitely you have to kind of go where the aircraft campaigns happen. So right now I'm looking at like impacts data and maybe Olympics, but there's opportunities to look at Arctic data as well with some of the recent campaigns that happened there.
Great, thank you.
You're welcome.
Right. Linda, go ahead.
Yes, thanks again for the presentations, both of you. Daniel asked my question for Jack, so then I will go for my question for Kaidi. Maybe I missed it, but did you also test your results for other regions, or did you now test it for one region?
Yeah, we counting test for 2 regions. So what I'm showing here is a kind of a smaller watershed than between my 2 regions. So I also have a test case for my relatively larger regions. But in terms of results, we can say because in my study here, we have 2 objectives. One is to look at how the precipitation uncertainty is retrieved from LSTM training. And second one, look at the streamflow prediction accuracies. But typically for the smaller watershed, the precipitation uncertainty retrieval is better since we have a stronger correlation between precipitation and streamflow in a smaller watershed. But for the streamflow prediction accuracy, the larger watershed will perform better because the larger watershed can generate a more smoother hydrograph compared to a smaller watershed. So that kind of a little bit of difference in the conclusion that we can make.
Yes, thanks. But you did not test it yet for another region, right?
Yeah, I'll be like trying to look at other regions to make the conclusion more stronger.
Okay, thanks.
Do still have a couple more minutes for questions if anybody has any more. All right. I think all my questions got covered. So if that is it, I suppose we can thank our speakers one more time. And once again, thanks to everybody for coming. Yes. And thanks to Kaidi and Jack for great presentations. And thanks everyone for coming. It was a excellent seminar. And like I said, look out for our third seminar, which will be coming up in a couple months. And then the fourth seminar is at AGU. So if you want to join us on social media or on our mailing list, feel free to do that. All right. Thanks.
Thank you.
Thank you.